In this video, you'll learn about, at a high level, spatial mapping, anchoring, and shaders. Computer vision for augmented reality, or AR, enables computers to obtain, process, analyze, and understand digital videos, images, and attributes. As you learned, by looking at an object and its appearance, location, and settings, a computer vision algorithm helps identify what the object is and gives additional context and meaning to end users. Let's look at some examples of how this is used for three-dimensional AR. Spatial mapping and anchoring are commonly used within AR experiences to understand the three-dimensional environment, and then to help position digital content in that 3D space. So think about it this way. Let's say you want to create an AR experience in which a 3D character is standing on your living room floor. First, the device you're using to experience the AR effect would need to understand where the floor is in the living room. How far in front of the camera is it? Where are the boundaries? Where does the floor hit the wall? The AR system will use an algorithm to collect and process these data points. Then you'd pinpoint a spot on that ground plane to position the character, which is the AR content. The character is now anchored to the room, with a coordinate system defining its position and rotation relative to the world. The AR system would continue doing calculations on every frame of the video, providing data points about the room. The data would include how the camera is moving, rotating, and translating, relative to the first image that was captured. The position of the character would update based on the estimated camera movement, so it always appears to be positioned on the same point on the 3D floor in the real room. Under the hood, the AR system estimates its motion using a process called simultaneous localization and mapping, or SLAM. On a very high level, SLAM builds up a map of the environment by tracking 2D points and images. Over time, it derives their associated 3D positions via parallax, which identifies the closer points versus the points that are further away. SLAM combines this with other sensor data to determine the trajectory of the camera over time. In the living room use case, the AR system might combine SLAM with a semantic segmentation algorithm to identify the floor in 3D. Shaders are another example of common algorithms that are used for AR graphics. Shader algorithms define how the surface of a 3D model should appear when composited into the real world: the texture, the color, the opacity, and more. Bringing this into context, think about a crystal ball and a ping pong ball. Both are spheres. However, the crystal ball is shiny, smooth, and mostly transparent, while the ping pong ball is matte, rough, and opaque white. Given a virtual object's pose relative to the camera, an AR shader's job is to create a rendering of the object that overlays with the actual image. This rendering might be combined with computer vision outputs to create unique AR effects. It's important for developers to know what shader inputs are provided by a given computer vision algorithm. One example is occlusion masking. Let's say you want to render an object behind a person. You might need to mask the object using a 2D segmentation map of the person. Or if you're rendering an object in a room in 3D, you might want to have the object look as if it's behind your furniture. To make this work, the algorithm needs to provide at least a rough mesh of the room, so that the shader can know which parts of the object shouldn't be rendered. An AR system may or may not provide this occlusion capability as part of SLAM. Computer vision plays a key role in AR experiences.